So our next speaker is Anamika Roy, and he's going to talk about quantifying patterns in the Vicsek model with topological tools.
Thank you. Hi, I'm Anamika, and I'm studying quantifying patterns in Vicsek model with topological tools. So my work is a bit different from the standard statistical physics approach. So I was a bit uncertain whether it will be accepted here or not. So Vicsek model is a very common model which was proposed in 1995, and several work has been done with this model. So for collective phenomena, so basically there is a point cloud and a random point cloud which moves with a velocity v, and the directions of the velocity is being influenced by the neighboring particles within a interaction radius r, and there is a noise perturbation eta. So this is a very simple model, but if you just play with the parameters like noise eta, the interaction radius r, the particle density n, so there will be a whole spectrum of different kind of patterns that would be generated. So my intention was to study this kind of patterns from this topological perspective. So studying dynamical systems and topology together has been a old approach, but it was not possible to apply all the kinds of theories of algebraic topology in real systems or simulated systems until last 2 decades. I think with the computational advances, it has been possible, and there is a branch called applied topology, where these different kind of studies are going on to study different kind of aggregation dynamics. These are some of the work that has influenced my work as well, with Topaz and Adams, who have been working to quantify the patterns in collective phenomena. So the basic idea of topological data analysis and pattern studies, there is a point cloud, and I'm trying to extract shape out of this point cloud. So for that, I need to build a cell complex or simplicial complex at different scales of resolution. So it's more like I'm looking at the point cloud with different kind of resolutions and what kind of shapes are being prominent. So there is a thing called persistent homology, where the idea is to the most prominent feature will be existing over long range of scales of resolutions, and the minute features will be disappearing after small scales of resolutions. So I was inspired by this idea and was trying to infuse in my work that I have been doing. So I'm trying to address this kind of questions that for this work. So how effectively can I extract the patterns or the summary of the patterns in my analysis? And the point clouds that I have been studying are temporary evolving. And so how do this pattern evolves? And how we understand the aggregation dynamics and how the parameters are responsible for these dynamics? And can we find any correlations between the topological transition that is happening and the classical order disorder transition that is already established? So for that, I have to, for time constraint, I will be giving a very brief introductions about the tools that I have used. So first thing is simplicial complex. There are different kind of simplicial complex that can be made. Simplicial complex is more like Legos cubes, or it's like I'm trying to make a shape out of a point cloud. And the tools, the cubes are the geometrical synthesis, which like points, line, triangle. It's like a higher dimensional analog of planar triangulations. So in my case, I was working with 2D point cloud. So I worked with alpha complex. The plus point of working with alpha complex is it's reduces the dimension. So for working with large particles, the computational time becomes less. So basically alpha complex is there is a point cloud and I'm building a ball of radius r. Suppose I'm interested to build a simplicial complex at scale r. So I'm building a ball of radius r around the points, and I'm also doing the Voronoi diagram or the Delanois triangulations. So if two balls are intersecting, then there is this line, and if there are three balls are intersecting and three Voronoi diagrams are intersecting, then there is a triangle. So in my case, the maximum dimension of simplices was 2 because it was a 2D point cloud. And so I have these point lines and triangles, and I'm trying to build shape out of these things. The parameters that I'm trying to study are the Beatty numbers and the Euler characteristics. So Beatty numbers gives us idea about the homological properties of the topological space that I'm trying to study. In simple terms, it's like the number of holes. So the innate Beatty numbers gives us the number of innate dimensional holes. So the 0-dimensional hole in topology is the connected component. The 1-dimensional hole are the loops or the circles. And the two-dimensional holes are the cavity or the voids that we see inside of in torus and donut-shaped objects. So the idea of, and there comes the Euler characteristics, which is the alternative sums of Betti numbers. Why studying Euler characteristics is important? Because it's a topological invariant. So as long as the topology of a shape remains unchanged, the Euler characteristics will be remaining unchanged. And this is like a very classical example. There are many examples available. So it's like if we just stretch a coffee mug, we can stretch a coffee mug to a donut-shaped torus. It's basically a continuous deformation of shape. So in topology, the number of holes matter more than the kind of shape we are looking at. So with that, I will be delving into the kind of analysis I have done. So this is like the right-hand side is the Betti curves, the evolutions of Betti numbers over time. Then comes the evolutions of Euler characteristics versus time, then the order parameter and the aggregate dynamics after sufficient number of time steps. So if we are increasing the noise from upper to top to bottom, and as we can see, as larger scales, so obviously they are all connected components, all components get connected given high particle density. But there is a thing, when there is an order achieved, the chi almost gets steady as similar time steps. Also the aggregate dynamics, if you look at the things, as we are increasing the noise, the flocking patterns or it's becoming from more dense aggregate to a porous or loopy aggregates. So order parameter alone cannot give us the kind of structural dynamics that is going on within the systems or within the flocking. And Betti curves is kind of a very good approximation or a tool to kind of quantify what kind of morphology I'm getting from this kind of tuning the parameters. Also, if we change the interaction radius r, I have kept the box length that L is equal to 1. So for very large radius of interactions, so there is a lot of interactions happening within this for this larger radius. So the chaos is somehow reduced. And for that kind of systems, the morphology is also changing, and that can be reflected in the Betti curves as well as this, we can quantify it. But again, studying all these Betti curves for different combinations of there are these three parameters: noise, interaction radius, and eta. So these will be very much overwhelming to get an insight from this kind of data, given all these kind of possible combinations that are happening. So we came up with a more compact mapping called Euler characteristic surface. So these are like variation of Euler characteristics over scales of resolutions and time. So the idea was, given 2-point clouds or two dynamical systems, if they are temporally evolving and their structures are very much different, topological structures, then those surfaces will be different as well. So these surfaces are kind of a footprint or signature of the dynamical systems that is happening. So if we change the parameters, the surfaces will be changing if the topology is changing as well. So we further tried to quantify with a metric called Euler metric between two surfaces. So how similar or dissimilar two different point clouds or two different dynamical systems are by these surfaces. So given two point cloud, we build their Euler characteristic surfaces and measure this metric distance called Euler metric. So in this case, I have kept the reference as this the surface with zero noise, and I have compared surface with different noise with the surface with zero noise, and also I have compared with the order parameter, classical velocity order parameter, and these are the graphs. So I have roughly segregated these graphs into three regions. In the order region, where there is much order in the systems, there is high fluctuations or high slope in these Euler metric curves. And when there is disorder taking place, so there is these competitions between noise and interactions, then the slope becomes a bit low. And in the complete chaotic region, where there is order parameter at its lowest, the Euler metric kind of saturates to its highest and doesn't change much, almost like a plateau-like region. So this clearly shows that there is a kind of a correlations between this topological transition and as well as this disorder transitions, which we are trying to explore further and quantify further. So this is how it stands now. So basically, given these Betti curves can give us a very good idea about the structural morphology that is happening in the swarm dynamics. And it's also very effective to it's kind of give us a rough idea about what is happening without looking at the snapshots. And this Euler metric clearly shows there is a relation between the topological transitions and the order disorder transitions. And in future, we are also planning to work with parameter recovery. So with this Euler metric thing, and can we recover a unknown, what kind of parameters are responsible from our unknown real data sets and all. So part of this work have been published with different dynamical systems in physics of fluids, and some part of this work in communication. So thank you for your attention. And I want to thank Professor Tapati Dattu, who I have been working with for the past few years, and Professor Atish Mitra from Tech Montana Department of Mathematics, who introduced me to the concepts of applied topology and all.